In each of the situations depicted below, two wave pulses move toward each other. One is bounded by points A and B. The other is bounded by points A prime and B prime. Draw what the combined pulse will look like when A and A prime are at the same point. Okay. Let's uncover a little bit of this so we can take a look. Okay, so now in the first scenario, we have two waves, okay, at each other. And so now what's going to happen initially is that B is going to, and there's really a total of 6 points if you think about it. There's this point here, 1, 2, 3, 4, 5, 6. So initially, point B here is going to meet A prime, but when these two wave regions completely overlap, then A and A prime will essentially be at the same position. Okay, so that's ultimately what we're trying to do. Now what we'll do is we're just going to kind of match these points up one point at a time. So for instance, is this one's going this way, this point matches with this point, point 2 matches with 2 over here, 3 matches with 3 over here, 4 matches with 4 over here, and so on. So that's what we're going to do. I'll call this 1, 2, 3, 4, 5, and 6 as well. Okay, so what I'm going to do is I'm going to draw in blue in the middle what it should look like. So now if I add these in, and the way we're going to figure this out, of course, is we're going to add the amplitudes. Now, since both waves are on the top of this string and they're approaching each other, they're going to meet and add constructively, okay? Meaning the amplitudes can be bigger. They're going to add together. So if I add the amplitudes of 0, you can see it's 0 because it's on that equilibrium position. So I'm going to add 0 and 2, right? And I get a 2. Now I'm going to put that over here on the far side because this wave right here essentially will have moved all the way over here and will have combined with this wave, which is going to move, oops, this one is going to move all the way over here as well. So ultimately I'm adding, you can see I'm adding these points in such a way where these two regions will overlap, okay? So if I add 0 and 2, I get a point of 2. So I'm going to plot a point of 2 right here. Okay, so it goes up to that point right there. Okay, and then my second point, 2, my number 2 here is at amplitude of 0, and then over here it's got an amplitude of 2. That would, of course, 0 plus 2 is going to add up to 2, so carry that across. And then 3, which is way up here, this has an amplitude of 2. This has an amplitude of 2. That means when they add together, it'll be an amplitude of 4. Okay, so I'm all the way up here now. Okay, then I'm going to add this region of 4, this region of 4. In fact, if you look, really, the last 3 points are all going to be 2 plus 2, 2 plus 2, and 2 plus 2. So that's going to be really easy to find the rest of this, which would be 4, 4, and 4. Right, and that would be the combined wave of how they interfere constructively. Okay, now you're supposed to draw it down below, so your drawing will look like this. Okay, but as you can see, it's essentially just taking this right here and just moving it down like that. But that's how you get this, is you're just going to point by point either add or subtract. So if they are constructively interfering, you add them. If they're destructively interfering, meaning they're on opposite sides, one point might be above the line, one point might be below the line, then you would subtract the points. All right, let's take a look at the next scenario. Okay, the next scenario is one of, well, let's just take a look at both. I can't really separate them anyway, so it's fine. Okay, so both are a case of destructive interference. Let's take a look at the middle case first. Okay, so again, we're going to start with our points here, and if you kind of number them like I am, so 1, 2, 3, 4, 5, and then back to 6 here, and this is 1, 2 is way down here, 3, 4, 5, and then 6 is way back here. So I'm going to add them. I'm going to add 1 with 1, 2 with 2, 3 with 3, 4 with 4, 5, 5, and 6, 6 as we go. And that's going to give me an idea of what the interference pattern should look like. Okay, so if I add 0 and 0, of course, I get a point of 0. So that's the first point there. My next point is going to be positive 2 coming from this way here. Okay, or no, positive, I'm sorry. It's the second number, positive 3. It has an amplitude of positive 3. Okay, and then this amplitude, which is also number 2, has an amplitude of negative 3. So those two would completely cancel, right, giving me a value of 0. Okay, now my next one, negative 3. Okay, so far this is kind of what I'm looking at. Okay, the first 3 points. Now the next one, which is labeled 4, that amplitude is positive 2, whereas this amplitude is negative 3. So 2 minus 3 is negative 1, I should expect. That. Okay, the next one, 5 and 5 here. You can see the first 5 on the left from the left waveform has an amplitude of 1. The 5 from the waveform coming from the right has an amplitude of negative 3. So 1 minus 3 is negative 2. And then lastly, 6 at 0.6 right there has an amplitude of 0. And then this, of course, has an amplitude of 0 as well. So we're back to 0 again. Okay, and then just taking a look at the next one. Okay, so if I'm going to number my points off, so 1, 2, 3, 4, 5, and 6 over here. 1, 2, 3, 4, 5, and 6. Okay, so the first one is going to be 0 amplitude and negative 2. So if I add those together, 0 minus 2 is negative 2. So I'm starting here. Now my next one has a positive amplitude of positive 1 and an amplitude here of negative 2. So positive 1 minus 2 would be negative 1. So I am down to here. Okay, and then here you can see at 0.3, we have a positive amplitude of 2 combined with a negative amplitude of 2. So that would be an amplitude of 0. So far that's what I have. Okay. At 0.4 on both sides, your amplitudes are 2 and negative 2 respectively. So that puts the waveform continuing like that. And then, of course, this one here has a positive amplitude of 1 at 0.5 here, and then 0.5 on the right has a negative amplitude of 2, negative 2, so 1 minus 2 is negative 2. Or, I'm sorry, 1 minus 2 is negative 1. Negative 1 brings me back to here. And then here at 0.6 here and 0.6 here, 0.6 on the left has an amplitude of 0, 0.6 on the right has an amplitude of negative 2. So if I take 0 minus 2, I get negative 2. So I'm back to here. And that's what they should look like down below. Okay, but I just wanted to show you guys piece by piece how you come up with these constructive interference and destructive interference overlapping diagrams. Section 20.7, sound. Important to note, sound is a longitudinal wave. I would either highlight this or underline it. That's going to be pretty key. Sound depends on the temperature of the air, but the accepted value is pretty close to 343. Now that's pretty much at room temperature, okay, so at around maybe 70 to 75 degrees Fahrenheit, somewhere around there. Colder temperatures result in slower speeds of sound. Explain the words ultrasound and infrasound. Okay, let's explain these. Humans can hear a range of frequencies from 20 to 20,000 hertz. Ultrasound, ultra means greater. So ultrasound frequencies are frequencies that are greater than human hearing. A good example of that would be a dog whistle. A dog whistle has a frequency higher than 20,000 hertz, so humans cannot perceive this sound. They cannot hear it. A dog, however, can, because it is in the range of hearing for a dog. Ultrasound frequencies are also used with pregnant mothers when they are going for their checkups, and you can basically take an image, in many cases nowadays a 3D image, but you can take an image using ultrasonic frequencies that reflect off the baby, and you can essentially take a computerized picture of what the baby looks like. Now, infra, if ultra means greater than, infra means less than. So infrasound frequencies are ones that are lower than 20 hertz. What wave quantities does loudness relate to? Well, loudness relates to the amplitude of the sound wave, the intensity of the sound wave. Section 20.8, pitch, frequency, and complex sounds. What quantity does pitch relate to? Well, pitch relates to frequency, okay? Frequency is what we measure, okay? Think of it that way. Frequency is a measurable thing. It is the number of cycles divided by the time it's been oscillating. Pitch, however, is what your brain perceives to be the frequency of that sound. So, for instance, a music teacher might refer to the pitch of somebody singing, right? Whereas a physics teacher would refer to the frequency of what is being measured. What is a fundamental? The fundamental frequency is the lowest and typically loudest, and you'll see this when you do your speed of sound lab a little bit later on. But it's the lowest, typically loudest frequency of a periodic waveform of a vibrating object, defining the primary pitch of that sound. This relates to what are called harmonics. What are harmonics? Well, harmonics are whole number multiples of the fundamental frequency. Okay, and you're going to see this play out in some of your initial labs that you're going to do coming up soon. Explain beats. This has nothing to do with rhythm. What it has to do with what must happen to cause the phenomenon of beats. Okay, well, let's take a look at that. A beat is a wave that results from the superposition of two waves at almost the same frequency. So for instance, if you had a wave at a frequency of 150 hertz and another wave at a frequency of 151 hertz, they're so close, but just being one cycle off every second causes there to be sometimes where they're in sync and then sometimes when they're out of sync. And so the in sync, out of sync, in sync, out of sync relates to a concept of something that is rhythmic. In other words, a beat. Okay. Now, again, a beat doesn't have anything to do with rhythm. The rhythm is just consequential. But let's take a look at what a beat might resemble. Okay. So if you look, the white wave above has a frequency of 15 hertz. That means there's 15 cycles every second. The green wave in the middle has a frequency of 16 hertz. So there's one more cycle per second for the green wave. You're going to notice, I want you to pay attention to the little red dot at the very, very top, okay, of each wave. Pay attention to when those dots are at the top of the wave together. Right now, both those red dots are at the very top, and thus the wave that forms on the bottom wave is formed out of either constructive or destructive interference. So I'm going to kind of pause this and kind of cue the video up. I'm going to let it run for a minute, and then I'm going to kind of move it around manually just to kind of show you points of constructive and destructive interference and how that relates to the alternating pattern that forms a beat. Notice where we were in constructive interference. Now those dots are completely out of phase with each other. Destructive interference. Now we're getting closer to being in sync again and perfectly in sync. Constructive interference, and now they're getting out of sync. And they're perfectly out of sync right now, destructive interference. So we can see it. Okay, starting, if I start here, okay, notice the white wave has the red dot at a trough, where the green wave has the red dot at a crest. They're completely out of phase with each other, and that results at the very bottom wave a case of destructive interference, which means the waves are kind of canceling out. Now, if we keep this pattern going, you can see that the white wave is catching up to the green one. Okay, slowly catching up. Green wave goes up, the red ball on the white wave goes up, and it's almost perfectly in sync. Right now, that little dot is exactly at the top of the white wave and the green wave at the same time. So we're going in and out of these regions of constructive and destructive interference. This forms a beat. Now, the beat frequency, and how do we calculate it? Well, the beat frequency is the difference in these two frequencies. So the difference in the frequencies of the example I gave you would be 1 hertz, right? 16 minus 15. Now, the absolute value bars here in the equation are there just to remind you that, if the first frequency, for instance, the first frequency was 15, the second one was 16. So if I go 15 minus 16, I get -1. The absolute value bars just remind you, take the absolute value. Don't worry about negatives, just the absolute value of the difference. So let's test our understanding on this one, okay? What I want you to do is I want you to pause the video, okay? 2 sound waves are broadcast at the same time as shown, in addition to their superposition. So you have wave 1, wave 2, and the superposition wave that forms. I want you to figure out, I want you to pause the video right now, figure out the frequency of wave 1, okay, the frequency of wave 2, and what the beat frequency would be combining these 2 waves. Pause the video and see if you can figure these things out. Okay, let's see what you came up with. Well, I'm going to zoom in here so you can see it. What I'm going to do is I'm going to focus my attention on this wave here. And what I did is I made some marks here. I don't know if you noticed my marks, but I made marks where the next cycle begins. So for instance, this would be 1 cycle. This would be 2 cycles. This would be 3 cycles. You see the pattern now. 4 cycles, 5, and 6. So I just kind of alternated between yellow and blue, just make them easy to stand out. But I counted 6 cycles. Now I'm going to keep going all the way to 1 second here just to make it easy, okay? So I'm going to keep going. There's 7 cycles. There's 8. There's 9. And there's 10. So that's why I made all those little black marks in there, because they indicate where the new cycle is going to begin. So I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 cycles per second, or 10 hertz. Frequency of wave 1 is 10 hertz. And it didn't matter. I could count here, I would get 10. I would count here, I would get 10. The frequency is constant, right, all the way through. Okay, now I'm going to look at wave 2. I'll choose 2 different colors here. So I got wave 1, wave 2. Let me go orange and red. Okay, so wave 1, wave 2, wave 3, 4, 5, 1, 2, 3, 4, 5, 6, 7, 8, 9. So I'm looking at one less cycle in the same 1 second time interval. So this would be a frequency of 9 hertz because there's 9 cycles in the 1 second. Now the B frequency would of course be the absolute value of 10 hertz minus 9 hertz, which is 1 hertz. What we find is the lower the beat frequency, okay, the slower the beat is. The higher the beat frequency, meaning the greater the difference between the two sounds, the beat frequency is much more rapid, and it sounds very rapid, rapidly repeating. Okay, and you can hear that sound. Okay, we're going to test our understanding again, okay, by looking at these strings. So we have a string with 8 beads attached carries a wave. The wave causes the beads to move. Each of the 4 cases shown below lead the wave to have velocities where the arrow is at a single instant in time. So for each case, circle the words that best describe the wave. Okay, now before we get into this is actually going to help us kind of understand the idea behind wave harmonics a little bit better, which is what's coming up to follow. Okay, so I just want to, this is kind of more like what your gut tells you. Okay, go ahead and pause the video and see if you can figure out these 4 scenarios. Is the wave traveling left, right, or is it standing in place? Okay, one thing you can rule out right now in each case is standing in place. And the reason you know that is because each wave has an up and down portion of it. To be standing in place, you must have a portion of the wave that literally is not moving up nor down. And that's not happening in any situation. So I could literally eliminate that as any possibility. Now, the easiest way to tell when a wave is moving to the right is the downhill portion, okay, is the uphill portion up and the downhill portion down? Is the uphill portion up and the downhill portion down? And that is the case right here. That wave is traveling right. Here, uphill portion is up, downhill portion is this time we have this portion up here that's leading, this portion over here is following. Since this is leading and this is following, the wave energy must be traveling left. Okay, now have a similar situation here. This is leading, going down, this is following, going up. Okay, we're again traveling to the left. And what I see in this scenario here is that this is going up, going down, going up, going down. And in that scenario here, it is leading the wave to go to the right. Now, if that doesn't quite make a whole lot of sense to you at the moment, that's kind of to be expected at this point. This is something that we have to generate with experience and a lot of models, okay? A lot of visuals to really get this. Okay. So in a few sentences, explain how to create a fundamental standing wave on a vibration. Okay, let me show you an example of a standing wave so we can get an idea of how to visualize this. Okay, so what I'm going to do is I'm going to show you a wave. So we have a wave, okay, that's coming in. Okay, now we have a red wave that is coming toward the wall. There's a wall there. It's a fixed end boundary, okay? And when it hits that wall, it's going to reflect. So we're going to see a blue wave reflection, okay? Let's take a look at the red wave, okay, and the blue wave as it results, okay? Right there, okay? Notice the blue wave is completely at the bottom. It forms a trough where the red wave forms a crest. And now a black wave is starting to form. The black wave is the addition and subtraction of these, okay, at various points. You'll see what I mean. Right now, at the very bottom of that wave, the blue wave and the red trough, the blue trough and the red trough have combined to make a much larger black amplitude. Keep going. And blue trough, notice what happened. The blue trough meets a red crest, and the black wave has come back down to 0. And it's forming these little portions that say N and A. Well, N stands for a node, which you will start to see is a region of the wave is not moving. It's a region of no maximum displacement at all. Whereas A stands for antinode, which is maximum displacement. So I'm going to keep this thing going so you can see. Notice where all the positions that say A, that's where the wave is getting really tall or really deep. And that's the result of construction interference. Look at all the A's, right? That shows you the tall black wave. Whereas if I let this go right there, notice every red wave is out of phase with its blue reflection, with the blue reflection before it. And now those spots all correspond to where it says N. Those are called nodes. And we can keep this going. Okay, now I'm going to take out the incident wave and the reflecting wave so you can see it. There we go. That is what's called a standing wave. A standing wave appears to do just what the name suggests. It appears to be standing in place, not moving to the left or right. The only reason it appears that way is because wave pulses moving one way are constructively and destructively interfering with the reflection from those pulses back against it. Okay, so that's what's forming these nodes and antinodes. So you must shake a rope upwards each time a previous wave pulse returns on its reflection. The amplitude of the disturbance, which is the interference, traveling along the rope grows larger. This is a standing wave with the first harmonic frequency. So the very first harmonic frequency doesn't even look like what we're seeing here. This, what we're looking at right here, 1, 2, 3, 4, 5, 6. This is the 6th harmonic frequency. The reason I know that is because if you count the number of antinodes, I see 6 antinodes. So however many antinodes you have corresponds to the frequency that you notice. Okay, here is another good illustration of string harmonics. Let me get rid of this. Okay, there you're looking at the fundamental frequency right there. Notice, kind of resembles jump rope, right? That's one harmonic. That's all we see is one harmonic. Now what I'm going to do is I'm going to put that down and I'm going to put that up. Now you're looking at 2 antinodes. You're looking at the 2nd harmonic frequency, right? So the number of antinodes, or big regions of maximum displacement on your wave, those correspond to the harmonic number of the frequency. Notice that point in the middle called a node. It's not moving anywhere. It's just staying in space. I'm going to now show you the 3rd harmonic, what that would look like. Okay, notice there are 3 antinodes separated equally by 2 nodes, right? And then finally, the 4th harmonic. I see 4 antinodes spaced out between 3 nodes. Explain how to create a 2nd harmonic standing wave vibration. Well, basically, you have to increase that frequency until we see 2 antinodes visible and 1 node right in the middle. What is a node and an antinode? So antinodes are specific points on a standing wave or air column that show maximum displacement. Nodes are the other points in between the, this is a typo. okay, in between the antinodes that do not show any vibration at all. So just a couple examples, right? This would be the first harmonic right here, one antinode, nothing more. This would be the second harmonic frequency, right? There's an antinode, there's a node in the middle, okay? Something like that. This would be the third harmonic. You can see one antinode, two antinodes, three antinodes, and two nodes separating them. Okay, boundary condition. A string can have many nodes and antinodes, but there must always be a node at the fixed end of any string. So one thing I didn't talk about is the fact that really there's a node at the end that I just didn't really consider. Okay, so each dot in the figure below represents the fixed endpoint of a string. Draw the harmonics indicated, write the letter A for each antinode, N for node in the diagram, properly spaced apart. For the symbolic columns, state the frequency and the wavelength in terms of L and the speed on the string. For the numerical columns, assume that L is 6 meters and V is 24 meters per second. Now we're going to do this for harmonic number 1, 2, 3, and 4. Okay. Now we have some work to do to set up this and actually have this make sense. Okay, so we're going to set up some of the work and some of the numerical work, and then we're going to come back to what the picture looks like. Okay, now I will start with the first diagram. Actually, I can start with the first two. The first two I think are very simple. The last three, though, need a little bit more care, so we'll figure out a way to make them work. Oh, but perhaps for the string, it's a little easier. When we start looking at standing waves and air columns, it's a little bit trickier. All right, so the first harmonic, we're going to go make a bulge that goes across like that. And then on the other side, we can indicate it with a dashed curve. Okay, there's an antinode, and I guess you could say those are two nodes right there. Now, what are you looking at here? This entire thing right here is length L. Okay, all of that is length L. So let's, at the very top, right up here where we have room, let's derive something together. One of the things we know is that V equals frequency times wavelength. We talked about that a while back. Well, if you solve that equation for frequency, frequency equals the speed divided by the wavelength. Now, we can also determine the wavelength in terms of what we see, like in terms of the length of the string. We know that the wavelength is the length of your oscillator divided by the number of cycles. That's how you find it. Okay, so I'm looking at here, I'm not looking at a full cycle, I'm looking at half a cycle. So in terms of the number of cycles, this is a half a cycle. Okay, now over here, I'll make a dot in the middle. I'm gonna go up, down through that dot, back up here. There's your second harmonic with two amplitudes right here, right, and three nodes. Always have one more node than an antinode, right? Okay, with three, should be pretty easy to do. I'll evenly space out right there. Got nodes here, and this would look like up, down, up, middle. Create the dashed curve that for the other side. And I've got three antinodes, sorry, and four nodes. Okay, now to get the last one, I'm splitting this in half. Okay, and then I'm splitting that in half, and then I'm splitting that distance in half, and I'm kind of going in between those. Okay, so I've got my 5 nodes. I'm gonna go up, down, up, down, up, and then the dash curve to complement. All right, so picture doesn't have to look perfect. Just try to get the idea of spacing, equal spacing. Okay, so I got 4 antinodes and 5 nodes. Okay, so what am I noticing here? For the first picture, I'm looking at a half a cycle. Okay, for the second picture, I'm looking at 1 full cycle. For the third picture, the third harmonic, I'm looking at 1 and a half cycle. So anytime it's just one antinode, it's a half cycle. Anytime it's two antinodes, that's one full cycle. So notice here I'm looking at one cycle, two full cycles. So the pattern kind of looks like this. We start off with a half a cycle, then 1.5, 2, and then so on. Okay, so I take the length of the oscillator divided by the number of cycles, and that gives me whatever the wavelength is. Okay, so I know that the wavelength for the first fundamental, I'm looking at half a cycle, so L would equal the wavelength divided by 2, which means lambda would equal to 2L. Okay, so the wavelength is 2 times that. So I'm just going to substitute that V over 2L. Okay, I'm going to put that here in the frequency column. So F1 would be 1 times V over 2L. You're going to see why did I put the 1 in there. You're going to see in a moment. Okay, symbolic wavelength. I kind of already did that right here, but let's do it again. Here, the length is equal to the wavelength divided by 2, so the wavelength would be 2 times the length of the oscillator. Okay, now the frequency, well, we can calculate it now. We're going to go F1 is equal to the speed, 24 over 2 times L, which is 6. So 24 over 12, 2 hertz. Okay, 2 hertz. Wavelength, right? We're going to go 2 times L, which is 6. The wavelength is 12 meters. Okay, so again, that should make sense, because if I told you this is half the cycle and half the cycle is 6 meters, that means the whole cycle, which we cannot see, the whole cycle, okay, would be 12 meters. Okay, for the second harmonic, notice what I'm looking at. Now I'm going to start with, because I'm trying to, basically in each case, I'm trying to substitute for lambda. So I got to figure that out first. I got to figure out this column first. So in this column, my length is actually equal to 1 full cycle, or 1 full wavelength. So here, my length is actually equal to lambda. But notice, I'm going to kind of make it look like this. If 1 wavelength equals 1 lambda, then that means 2 lambda is equal to 2 times the length. And why would I be doing this? Because if I can write it like this, where lambda equals 2L over 2, and substitute that right there in place of lambda, okay, then here's what I get. I get V over the wavelength, which is going to be V over 2L over 2. But if I divide by 2L over 2, I'm really multiplying by 2 over 2L. So it's 2V over 2L. Okay. In the case of the third, I'm looking at the whole length is now 1.5 cycles, or 1.5 wavelengths. The whole length is 1.5, or 3/2 of wavelength. That means the wavelength is now, if I multiply by 2 and divide by 3, it's 2/3, or 2L over 3. So I'm going to take that and plug that right here. So, this was supposed to be F2, sorry. So F3, okay, is going to be V over 2L over 3, which would be 3V over 2L. Notice the pattern. Notice everything else is the same. Okay, next one, we have the length of the oscillator is equal to 2 full wavelengths, 2 full cycles. So the length of the oscillator equals 2 lambda, or lambda equals L over 2. Okay, now I kind of want things to stay the same with a with a 2L in there. So what I'm going to do is I'm just going to kind of rewrite this as if lambda is equal to L over 2, it's equal to 2L over 4. 2/4 is the same ratio as 1 over 2. So I'm going to plug that right in here. And I get V over 2L over 4, which would be 4V over 2L. Still follows the same pattern. Okay, so you can see from the pattern here, each harmonic frequency is just going up by an integer multiple. In other words, the fourth harmonic is 4 times V over 2L, and V over 2L is the first harmonic. Right? The third harmonic is just 3 times this value of V over 2L, which is the first harmonic. So one of the things I should be noticing here is that any frequency is going to be the original frequency times the integer multiple. Okay, so that's how I can, that is a little shortcut. That's how I can find the frequency of any. So let's go ahead and fill out the mathematical portion. So F2, I'm just going to use this for simplicity. It's going to be V, which is 24 over 6, which is going to be 4 hertz. And that's fitting the pattern so far, because what should I be seeing here? 2 times 2 hertz is 4 hertz. Okay. Whereas the wavelength? The wavelength is 1 cycle, right? It is the length, which would be 6 meters. Okay, F3. We're going to go 3V, 3 times 24 over 2L, 2 times 6. I could reduce this. 12 goes into that 2 times, and then if I multiply that, I get F3 equals 6. Right, again, should be seeing the pattern. Right, because now I'm looking at the third harmonic, which is a multiple of 3, integer multiple of 3 times the original frequency of 2, which gives me 6 hertz. Okay, the wavelength is equal to 2L over 3. 2 times 6 over 3. 3 goes into that 2 times, and we're getting, what, 4 meters? So you should be noticing that the wavelength is going down each time. Okay. All right, F4, we're going to plug in a 4V over 2L, so 4 times 24 over 2 times 6. I can cancel that by going 12 into 24 2 times, and 2 times 4 would give me 8. And I should have been able to predict that anyway. You can see it's going up by integer multiple of 2 each time. Okay, and that final wavelength is L over 2. Yeah. So 6 over 2 would be 3 meters. And we do expect it to go down because the frequency is going up. Okay. Standing waves in an air column. So at an open end of the pipe, the sound waves must have a what? Antinode or a node? And same thing at the closed end of a pipe. The sound waves must have what? An antinode or node. Let's take a look at an image that would help you make this determination. Okay, so we have standing longitudinal waves. I'm going to start with a pipe. It's called an open pipe, okay, because that's open at both ends, as opposed to a closed pipe, where you can see now it's closed at the left end. Okay. Now, I want you to notice something about this. Look at the 3 dots in the middle. Well, they don't move very much, left or right. And that corresponds to the displacement diagram below with a node. So the nodes for an air column, at least for the first fundamental frequency, are found right in the middle. Whereas the air molecules are able to move a lot, left and right, at each end. Those correspond to antinodes. When we close off one end, you're looking at nodes at the closed end, and that should make sense because the molecules can't move very much at the closed end. Whereas at the open end, they have maximum space to move, so they're going to have maximum displacement. So we have a node at the closed end and an antinode at the open end. Open end must have an antinode. Closed end of the pipe must have a node. Okay, now we're going to focus on harmonics 1, 2, and 3. Now for this one, with the pipe drawings, because we're going to start with an open pipe, these ones are a little bit more challenging to space them evenly apart. So we're going to mathematically determine what they look like first. The first harmonic typically looks like this. So it'll be something like that, where you're going to have you'll have an antinode here, an antinode here, and a node here. But what are we actually looking at? If you remember from the fundamental string drawing, this was half a cycle, half a wavelength. So the length is half a wavelength. Okay, but notice something about this. This drawing is actually the same as this drawing. Okay, here's what I mean by that. This portion here looks just like this portion here. And this portion here looks just like this portion here. It's just been, it's the same wave, but it's been disconnected and kind of oriented back to back rather than kind of looking, right at each other. So this is this fundamental frequency for an open pipe. It begins to follow the same pattern. Now, for the next harmonic, that's for the first harmonic. The second harmonic, we're going to have to place a couple nodes apart, and we're going to have to go like this, so that you have an antinode, 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 node, node. Okay, now what am I looking at here? Notice this whole thing is half a wavelength. So if I cut that in half, this is a quarter, and this is a quarter. Okay, so a quarter plus quarter is a half. So I'm looking at a quarter of a wavelength and a quarter of a wavelength to give me 1/2 a wavelength. Well, what am I looking at here? I'm looking at a quarter of wavelength, a half a wavelength, and a quarter of wavelength. So for this one, L equals a quarter plus quarter is a half, plus another half is 1 full wavelength. That is matching exactly what we saw here with the second harmonic. Antinode, antinode, node, node, node. This was 1 full cycle, just like we're seeing here. Okay, and then the third harmonic that we're going to encounter is going to look like this. Instead of having just 2 nodes inside, you're going to have 3. So you have one in the middle, one out here, one out here. Like that. And like that. So we have antinode, 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 node, node, node. And we're looking at what? This is a quarter wavelength. Here's a half. Here's a half. There's a quarter. Well, a quarter plus a quarter is a half, plus a half is 1, plus another half is 3 halves lambda, or 3 lambda over 2. So it's following the exact same pattern that we saw with the strings, right? This one was showing you one cycle and a half. 1.5 is 3 halves. So what I'm going to do in order to make the drawings kind of look a little better, I'm going to figure out the numerical part of it first, okay? So since everything mimics exactly what we saw with the string conditions, like exactly, then this is going to be very easy for us to do. So for the first one, the length equals half a cycle, which means if I solve for lambda, multiply by 2, the wavelength is 2 times the length. So if the fundamental frequency is equal to V over lambda, it's going to be V over 2L. Okay, this would be 300 over 2 times 3, because the length is 3. Okay, this will be doable to evaluate. So 3 goes into 300 100 times, and then 100 divided by 2 is 50. So F1 should be 50. Now, if you were paying attention to the patterns we saw earlier, you'll know that the other frequencies are integer multiples of the first. So the second harmonic is 2 times the first, or 2, in this case, 2 times 50, right? So we should expect the second harmonic to be 100 hertz. We should expect the third harmonic to be 150 hertz. So once you learn that first one, it's easy to find all the others. Okay, the wavelength, wavelength is 2 times the length, or 2 times 3, or the wavelength is 6 meters. Okay, for the next one, the length is equal to the wavelength, which I'm going to write as 2 lambda over 2. Okay, you'll see why I'm doing that in a second. So the second harmonic, V over lambda, but it's V over, if I multiply both sides by 2, 2L over 2, which is the same as 2V over 2L. So 2 times 300 over 2 times 3. Okay, that goes into that 100 times. That cancels, and clearly we can see we get 100 hertz. Okay, L equals lambda equals 2L over 2, or just lambda equals L, which is going to be 3 meters. Okay, and for the last one, the length was equal to 3.5 cycles, or lambda is equal to 2L over 3, okay, 2/3 of the length. So V over 2L over 3 would be 3V over 2L. So 3 times 300 over 2 times 3. Yeah, so 3, okay, we could do this a couple ways. 3 cancels with 3, and then 2 goes into 300 150 times. Right, very predictable pattern, just exactly what we said it would be. Okay, you should be able to figure out that the fourth harmonic would be 200 hertz, the fifth one 250, and so on. Okay, now the wavelength in this case is 2L over 3, or 2 times 3 over 3. The 3's cancel, so the wavelength is 2 meters. All right, so what's the wavelength for the first one? The full wavelength is 6. So for the first one, it's actually easy to draw because I'm drawing a node in the middle, just like that. an antinode here, and an antinode here. So it's going to go like that, and then use a dash line to get the other side. So there's an antinode, there's an antinode. Okay, I'm looking at a quarter of a wavelength here, and a quarter of a wavelength here. So quarter plus quarter, right? The length equals half a wave. Okay, what am I looking for in this case? The wavelength is 3 meters long this time, not 6. So let me see, the 3 meters would be 1, 2, 3, full cycle. Okay, so half a cycle would be 1.5. Okay, so 1.5, 1.5. We gotta count up the spaces here. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we got 10, and then it's 1, 2, 3, 4, 5. So 1, 2, 3, 5, something like that. Okay, more or less, it's going to look about like this. Okay, where you're going to have like this, that. Okay, and we have antinode, 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 node, node. We're looking at a quarter of wavelength. We're looking at a half a wavelength. We're looking at a quarter of wavelength. Quarter plus quarter is half, and then of course plus one more half is, well, 2 over 2. It's 1 whole. Okay, now in the last one, I need the wavelength to be 2 meters on that one. Okay, and I could probably have it looking like this. 1, 2, 3, something like that. Okay, so antinode, 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 node, node, node. I'm looking at a quarter of a wave. I'm looking at a half a wave. I'm looking at a half a wave, and here I'm looking at a quarter wave. So quarter plus quarter is a half, plus a half is 1, plus another half is 1.5. That's exactly what we see here, where the length is 1.5. Okay, so that is what it should look like for an open pipe. Now for closed pipe, things are a little different, okay? Let me show you why. I'm gonna start off with the first one. So we're still gonna do first 3, okay? I have a node at this end. I have an antinode at that end. So I'm gonna draw a curve up here, but I'm gonna draw a dash curve down there. And what we're looking at is we're looking at 1/4 of the wavelength. The entire length is equal to 1/4 of the wavelength this time. So if length equals lambda over 4, that means lambda equals 4L, not 2L like it did before. So F1 is equal to V over lambda, or V over 4L. There's our fundamental frequency right there. Okay. Numerically speaking, what would that look like? So V is 300 over 3, looking at what, 100 hertz? Okay, wavelength is 4 times the length of the oscillator, which is still 3 meters. Okay, so that would be 12 meters. Okay, now for this one, this is where it gets a little tricky with the closed pipe because it's not so evenly symmetrical like strings and open pipes have been. All right, let's numerically figure this out, okay? Now, I know for the second harmonic, okay, I need to have 2 nodes and an antinode. So where here I only have 1 node and an antinode, I need to have 2 nodes and an antinode. So I'll have a node here for sure. I'll always have a node there. Okay, but now I need another node a certain distance apart. So what I'm looking at here, my sketch for the next harmonic is going to look kind of like this. I got node, node, and an antinode like that. So I mean something like that. Okay, I'm trying to figure out how to space it right now. So I got a quarter of a wave, half a wave. So half plus a quarter, the length would equal 3/4 of a wavelength, which means the wavelength would be equal to 4L over 3, or 4/3 the length, or 1 1/3. Okay, that would be, I'm going to call it F2, that's V over lambda, or it's V over 4L over 3, which means the next harmonic is 3V over 4L. That's kind of weird because normally the pattern we've seen has been it's just kind of going up by integer multiples, right? 1, 2, 3, 4, 5, 6. But it skipped the number 2. It went from 1 to 3. Okay. Now numerically speaking, the frequency would be, for the second one, 3 times 300 over 4 times the length of 3. Okay, we have 3 goes into 3 ones, and 300 divided by 4 gives me 75. So the next harmonic should be 75 hertz? No, hold on. I don't think I did that right. So 300 divided by 12. 25. There we go. That's not right either. Okay. 300. Okay, so the wavelength is equal to 4 times 3 over 3. Okay, so that cancels. Okay, got that part right. Okay, and we're looking at 4 meters there. Okay. And if I go 300 divided by 4 times 3, that's where I went wrong. Okay. So 100 is 300. That's where I went wrong. This is not 100. Okay, my apologies. Okay, so let me fix this. It's V over 4L, so it's going to be 300 over 4 times the length of 3. So 300 divided by 12 is 25. That's better. Okay. Now it's making more sense. My apologies there. So here, what are we looking at here? The 3's cancel, and then 300 over 4 is 75. That's making more sense because we can see that this is an integer multiple of 3 times the original, and 3 times 25 is 75. So that's how it should be working.